In the previous lecture, we learned the definition of a series. We know a series is the sum of an infinite sequence. We also look at two examples. One example, the sum goes to infinity, and the other example, it shows that the sum of infinite terms equals to 1. For most of the time, it is hard to find the finite value, the sum of a series. But there's a special series called the geometric series. Under some conditions, we are able to find the finite sum. Let's look at the geometric series in this lecture. A geometric series is a series that could be expressed in this form: a plus a times r plus a times r squared, and so on. In sigma notation, we can also write the geometric series as the sum of a, some constant, times some common ratio, r to the power of n minus 1, or n starting from 1. And this series is called a geometric series if and only if the initial value a is non-zero. Now let's find the explicit form of the sum of this series. Let's look at two cases. If the common ratio r equals to 1, then the partial sum is a plus a times 1, which is still a. Then the third term, a times r squared, but r equals to 1. And 1 squared is still 1. So the third term is still a. And we do that until we get to plus a times r to the power of n minus 1. But r is 1, so r to the power of n minus 1 is still 1. So here we have n terms. So the partial sum equals to n times a. And we can note that this term is approaching to plus or minus infinity, depending on the sign of a, as n approaches infinity. So the geometric series diverges in this case. How about the second case? If r does not equal to 1, then the partial sum, Sn, it will be a plus a times r plus a times r squared plus until we get to a times r to the power of n minus 1. I'm going to write down a second equation for r times the partial sum, Sn. Then this equation equals to a times r plus a times r squared plus a times r cubed until plus a times r to the power of n. I'm going to call the first equation, equation 1, and r times the partial sum as equation 2. And as you can note that the first term in the second equation equals to the second term in the first equation, and the second term in equation 2 is the third term in equation 1. And I can pair all the terms like this. So the last term in equation 1 will be the second to last term in equation 2. Then if I do equation 1 minus equation 2, then the terms that I circle in purple, they will cancel each other out. So I'll be left with Sn minus r times Sn. That is the left-hand side of equation 1 and equation 2. And this equals a from equation 1, then minus the last term in equation 2, a times r to the power of n. Then from here, I can isolate for the partial sum, Sn. Sn equals, on the right-hand side, I can factor out the a, and I'm left with 1 minus r to the power of n. And I divide it by the terms that I factor out on the left-hand side, which is 1 minus r. Then, if the absolute of r is smaller than 1, then r to the power of n converges to 0. So, the limit as n approaches to infinity of the partial sum Sn, which is the limit as n approaches to infinity of the expression that we just found, a times 1 minus r to the power of n divided by 1 minus r. But since r to the power of n converges to 0, so we'll be left with a divided by 1 minus r. How about if absolute of r is greater than 1? Then r to the power of n diverges. So the sequence for the partial sum, Sn, also diverges, which also means the geometric series when the common ratio absolute of r is greater than 1 diverges. So sum for n starting from 1 of a times r to the power of n minus 1 diverges. So just a quick reminder, we've looked at two cases. In the second case, we separate into two more cases. The first case is when the common ratio is 1, and we found that the partial sum diverges. And the second case is when the common ratio r is not 1, and we found that if absolute of r is smaller than 1, then it converges, and we can actually find the finite sum of this geometric series. But if the absolute of r is greater than 1, then the geometric series diverges. So if we combine all the conditions, we can note that the geometric series only converges if the common ratio absolute of r is smaller than 1, and it converges to this value, a divided by 1 minus r. Otherwise, if absolute of r is greater than 1 or equals to 1, the geometric series diverges. Here it shows the summary of how we just proved. A geometric series is a series that can be expressed in this form. It has some initial value a and a common ratio r. And we express this sum as a times r to the power of n minus 1. We found that the geometric series is only convergent if absolute of r is smaller than 1, and its sum, we found that it equals to a divided by 1 minus r. Otherwise, if absolute of r is greater than or equals to 1, then the geometric series is divergent. Let's look at example 1 below. Find the sum of the geometric series 5 minus 10 divided by 3 plus 20 divided by 9 minus 40 divided by 27, and so on. We can note that it is a geometric series with the first term a equals to 5, and to find the common ratio, we can take the second term divided by a, which is negative of 2 divided by 3. We could also verify that with the third and the fourth term. Are they equal to a times r squared and a times r cubed? The answer is yes. So this is a geometric series. Then we can note that the absolute of r, which is 2 divided by 3, is smaller than 1. Then from the summary, we know that this geometric series converges, and we can explicitly find the sum of this series. The sum for n starting from 1 to infinity of 5 times negative 2 divided by 3 to the power of n minus 1 equals a divided by 1 minus r, where a is 5 and r is negative 2 over 3, which equals to 5 divided by 5 over 3. So this geometric series converges to 3. Now let's look at the second example. Is the series convergent or divergent? We note that in this series, the n's are in the exponents, so we could use exponential rules and rewrite this series as geometric series. So we have sum for n starting from 1 to infinity. The first term, I have 2 to the power of 2n. I can rewrite that as 2 to the power of 2, then to the power of n. Then I have 5 to the power of 1 minus n. I can rewrite that as 5 times 5 to the power of negative n. And the last term, I have negative 1 to the power of 3n. I can rewrite that as negative 1 to the power of 3, then whole thing to the power of n. Then this equals sigma for n starting from 1. Note that only the 5 do not have an exponent to the power of n, so I can pull this constant to the front. 5. Then I have 2 to the power of 2 and to the power of n, which is 4 to the power of n. Then I have 5 to the power of negative 1, which also equals to 1 over 5 to the power of n. And lastly, I have negative 1 to the power of 3, which is negative 1. Then this to the power of n. And finally, I can combine the terms with power of n. So this equals the sum for n starting from 1 of 5. Then I multiply the other base, which is negative of 4 divided by 5, and this to the power of n. But note that in the geometric series, we had n to the power of 1. But here I only have to the power of n. So I want to rewrite this series so that the exponent is n minus 1. I can do that by factoring out one time of the common ratio. So this equals the sum for n starting from 1 of 5 times negative 4 divided by 5 to the power of n minus 1, then times the common ratio, negative 4 divided by 5. Then I combine the two constants, the 5 and the negative 4 divided by 5, which equals the sum for n starting from 1 of negative 4 times negative 4 divided by 5 to the power of n minus 1. Now I have the series in geometric series form with a, the starting value, equals to negative 4, and the common ratio, r, equals to negative 4 divided by 5. We note that the absolute of r is smaller than 1. So we know this geometric series converges. So the sum for n starting from 1 of 2 to the power of 2n times 5 to the power of 1 minus n times negative 1 to the power of 3n should equal to a divided by 1 minus r. A is negative 4. Then divide this by 1 minus, and r is negative 4 divided by 5, which equals negative 4 divided by 9 divided by 5, which equals to negative 20 divided by 9. Now let's look at the last example. Find the sum of the series, sum of xn for n starting from 0, where absolute of x is smaller than 1. Similarly to example 2, we notice that the n is in the exponent, so we should be able to rewrite that in geometric series. But in geometric series, we have a series for n starting from 1. But notice that here the n starts from 0. Also note that the exponent we have n, but the geometric form we had, the exponent is n minus 1. So we have to rewrite that. You can use the exponent rules just like example 2, or we can write out the first few terms. Then the first value would be the a, and the second term divided by the first term would be the common ratio. Let's do that in this example. So we have sum for n starting from 0 of x to the power of n. Let's expand this series. The first term when n equals to 0, x to the power of 0 is 1. Then plus, when n equals to 1, we have x. Then the third term, when n equals to 2, we have x squared, and so on. So we notice that the starting term is 1, which means a equals to 1. And the common ratio, the second term divided by first term, equals to x. So this series also equals to sum for n starting from 1 of 1 times x to the power of n minus 1. So this is a geometric series with a equals to 1 and r equals to x. and it was given in the problem that absolute of x is smaller than 1, which means absolute of r, which is also absolute of x, is smaller than 1. So we know that this geometric series converges. So absolute of r, which is absolute of x, and from the problem, we know that absolute of x is smaller than 1. So this geometric series converges. The sum for n starting from 0 of x to the power of n equals a divided by 1 minus r. A equals to 1 and r equals to x. So this series converges to 1 divided by 1 minus x. And that is the end of the lecture. In the next lecture, we are going to look at another special series, which is called the telescoping series. That is when we have terms that can cancel in pairs.